Welcome to day 22 of the 2023 Advent of Code. So for today's problem, we have a bunch of bricks of sand, and we're going to need to disintegrate some of them. We have a tall stack, and we need to be careful about choosing which bricks to disintegrate, because portions of the stack could topple if we disintegrate the wrong one. So we get a snapshot of the bricks while they were still falling. And so this is our input. We're given x, y, z coordinates, and this represents a rectangle in that space. We'll be given two opposing corners of the brick separated by a tilde. And so each brick is made up of a single straight line of cubes. And so what that means is that basically two of the coordinates will be the same and the last one will be different, meaning that we won't have any like 2x3 bricks. I'm not going to take any advantage of this optimization though. Okay, and so the elves also chose a time such that all of the snapshots were integer positions, so they're all aligned to the grid. And each of the cubes is also an integer width, height, and length, and so we don't need to worry about anything except integers here. If the line shows two of the same coordinates, it just means that the brick is a single cube. These lines are both horizontal, and this would be a vertical brick. So basically the z coordinate is actually the vertical. So it's not the y coordinate, it's the z coordinate that's vertical, so just be careful with that. The ground is infinite and perfectly flat at z equals 0, and so the lowest z value a brick can have is 1. And so these two bricks with their z index of 1 and this vertical brick with a z index of 1 to 5 are both resting on the ground. But this brick would be above the ground at the time of the snapshot. Some of the bricks are still up in the air and completely unsupported, so we'll need to start by figuring out where they'll end up. The bricks are stabilized so they'll never rotate, even if a long horizontal brick is only supported on one end. So if we bring out the whiteboard, basically if we have a brick that's like this and it falls onto another brick like this, it will not topple, it will just stay floating like this. And so here's a diagram of our example. So again, z is vertical, and here it is with this x horizontal, and here's the cross-section from the other angle with the y horizontal. So we see here that A is at the very bottom, and it is supporting B, and C is actually not supported by B because it is behind B in the y space, and so it will fall down by 1. As a result, after C falls down by 1, D will also fall down by 1, and since here we can see that E is behind D in x space, E is not supported by D, so it'll fall down by 2 so that it rests on top of both B and C. And then etc., so on and so forth. So basically, the way we can visualize this as somewhat of a Jenga tower, I guess, is we have A that looks roughly like this, and then we have B and C resting on top of it, like so. And then we have D and E resting on top of those across. Pardon the poor drawing skills. And then finally we have F, which is perpendicular to A, resting on top of those two. And so that's roughly what our stack looks like. And then we also have G, which is a vertical along the middle, and so it will stand up on top of F like this. So this is what the stack will look like once everything falls down to the bottom. And so once all of them fall as far down as they go, this is what the stack looks like. This is what we've drawn in 3D. I apologize, it's a bit hard to see what's going on here. But now once they've all settled down, it's easy to tell which bricks are supporting other bricks. So we see that A is supporting B and C, and it's the only one supporting B and C. So if it got disintegrated, B and C would both fall. And then that would cause a cascade. If B is disintegrated, nothing happens because D and F are both supported by C as well. And likewise, if C is disintegrated, nothing happens because B and C are both sharing the support. Likewise, D and E are both sharing the support for F, so both of them can be disintegrated. F, however, is the only supporter of G, and therefore it cannot be disintegrated. And finally, G can be disintegrated because it's on top and not supporting anything else. So our task for part 1 is to figure out how many bricks can be disintegrated without causing any more falls. So the way we're going to approach this is first we're going to read in all of the bricks. Then we're going to drop all of them down into their positions, and then we will form a map of which bricks are supporting which ones. So we'll want to know for each brick, which ones are it supporting, and for each brick, which ones are supporting it. And then for each brick, we know that it can be safely disintegrated if for all bricks that it's supporting, that brick is also supported by something else. So basically, if our brick is not the sole supporter of any other bricks. So let's first take a quick look at the input size. So if I disable Zen mode for a bit, we can see that the input goes to about 1,500 bricks. So what that tells us is we can use an O of n squared algorithm because 1.5 thousand squared is about 2 million. And so that's reasonable for a loop. However, if we try to do n cubed, then it probably won't work. So first let's grab our inputs. So bricks, we're going to store it as an array of length 6 arrays. And the reason we're using arrays instead of tuples on the inside is because we want to be able to mutate the value so we can drop the bricks a bit more easily. Using tuples is fine, but it's just not necessary. So we're going to say line for line in open is 0. Now for each line, we're going to transform the tilde in the middle to a comma, and then split on the comma. And then we're going to map int over that result. And so now we will get an array of length 6 arrays. Now we want to sort them in ascending order, and the reason we want to do that is so we can make the processing a bit easier. So each time we drop a brick, we only need to see if it intersects with bricks below it. We don't need to check anything after in the list. So we're going to sort them by the Z value. So we're going to say bricks.sort, and we want to sort by the Z value, which is stored at index 2. So our key will be lambda brick at index 2. So now if we print our bricks, for the test input nothing changes because they were already given in ascending order. If we print for our real output, we can see that now the Z value is non-decreasing. The X and Y values don't matter, so I'm not going to bother sorting by them. Now we're going to go through and drop each brick. So for index in ranged length bricks, we can start at index 1 because the bottommost index might be able to be dropped. So for each brick, we're going to keep a running maximum or minimum of how far down it can fall. So if we assume there are no bricks below it, it can fall all the way down to a Z index of 1. So we'll use MZ, or let's just call it maximum Z, the maximum Z value it can have after it drops as far down as it will go. So now we want to look at all of the other bricks. So for all bricks below it, for brick in, actually we'll call the current brick, or we can actually get this using a enumerate. We'll call the next brick check. So for check in bricks up until and not including the index, we're going to see how far down it can fall. So we first need to check if they intersect, or rather overlap each other. So basically, if we look from the top down, will they even touch each other? Because if not, then they don't affect each other as they fall. So let's create a function called def will intersect, or just overlaps, I guess, for given bricks A and B. So the way we can check if two rectangles overlap, because that's all we're doing here. Given two rectangles, they intersect if and only if their x ranges intersect. So this is the x range of the first rectangle and of the second. If their x ranges intersect and their y ranges also intersect, that's the condition for rectangle intersection. And from previous problems, and I can link a short on interval manipulation, which gives the reason for why we can do this. The way we check if two ranges intersect is we check if the lower value of each range is less than the higher value of the other range. So if the start of each range is smaller than the end. And so the way we can do that is we can just say if the maximum of the first and second starts is less than, or in this case less than or equal to, the minimum of the first and second ending positions. So here we are ignoring Z because we're just checking from a bird's eye view whether or not there's going to be an overlap. And so the condition is if the x value of A, so if the maximum of the starting x values is less than or equal to the minimum of the ending x values, and the maximum of the starting y values is less than or equal to the minimum of the ending y values. So now we can say, if the brick overlaps with the check brick, then we need to make sure that this brick does not fall beyond this brick. And so if check has a Z position of check 3, so that's the top Z position. So if the brick is vertical, it'll be the top position, otherwise it's just the same as check 0. The maximum Z value we can fall down to is going to be this plus 1 because it needs to rest neatly on top of it. So basically if our check has, let's say 2, 3, 4, if our check has a top Z value at Z equals 4, then our brick can only fall to that plus 1. So we can say max Z equals max of the value and check 3 plus 1. And then we can drop the brick down to max Z. And so we're going to do brick 0 equals max Z. We're also going to want to adjust 3 by the same amount. And so the amount we're adjusting by is plus max Z minus brick 0. That's the adjustment amount, because we can see that if we add that to brick 0, the first and last terms cancel out and we just get max Z. So we're going to say brick 3 plus equals this difference. And obviously this difference will always be non-positive. We could also do minus equals brick 0 minus max Z. This might make a bit more sense. Basically, how far does it fall? And we're going to subtract this from the top of the brick as well. So now we're going to want to sort our bricks again because they might have fallen out of order. And now let's print out our bricks. Oh yeah, that didn't work. Reason is because I forgot that when I was solving this problem myself, I had my items in a different order. So my apologies, this is supposed to be 5 and 2. That's where we store the Z coordinate. Okay, so now if we run it, we see that our bricks have successfully fallen. So this is the A brick. It's still at Z index 1. B is still at Z index 2, but C has now also fallen to 2. D and E have each fallen down to 3. F has fallen to 4, and G is now sitting on top of F at index Z equals 5 up to 6. So now that we've simulated the bricks falling, we're going to get a map of which bricks are supporting which bricks. So we're going to need 2 dictionaries pointing from each index to a set. We're going to use indices because it's probably a bit more efficient than trying to tuple the lists and sort them as the keys. And it's not going to be particularly counterintuitive. So we're going to say key supports value equals a dictionary from I to an empty set for each index. And then we're also going to do the same for V supports K. So the first one means that I will support everything in its set. The second one means that everything in this set supports I, basically. So now we're going to go through each pair of bricks. And also note that we only need to check the bricks in one order because our bricks go in ascending order. So a brick can only possibly support one that comes after in the list. And so we can say for I lower in enumerate bricks. And then for J higher, we'll call upper in enumerate bricks. For I lower in enumerate bricks up to that index. The reason we have to do it this way and not the other way around is because if we did it the other way around, then the enumerate index would get offset. And although we could fix that here, it's just a bit more intuitive to do it this way around. So now we check. If they overlap each other, then that means that they are vertical. They coincide when we look at them vertically. And the lower one supports the upper one if and only if the upper one rests directly upon it. So it is also required that the bottom z coordinate of the upper block is exactly equal to the top z index of the lower block plus 1. If this is the case, then the lower brick supports the upper brick, so the lower brick, which has index I, supports the upper brick, and the upper brick is supported by the lower brick. So if we print out K supports V, we see that A supports B and C, B and C both support D and E both support F, and F supports G, and G supports nothing. Likewise, if we turn this around, we see that A is supported by nothing because it's on the ground. B and C are both solely supported by A. D and E are both supported by both B and C. F is supported by D and E, and G is supported solely by F. And so now we can just go through each index and see if every block that it supports is also supported by something else. So our total starts at 0, and we can say for I in range length of bricks, if it is true that for all j in K supports V of I, so basically if for each brick that's supported by our current I, the length of the number of supporters of j is greater than or equal to 2, meaning it has more than one supporter, then this block can safely be disintegrated because everything that it supports is also supported by something else. So we can disintegrate it, and that will give us the number of bricks that we can disintegrate in total. We can optimize this slightly by, instead of storing a set here, we can just store the length directly. So you can just say I 0, and then instead of add I, we can just say plus equals 1. And now we can remove the length requirement here. And so that doesn't actually save any runtime, so we'll keep it here because storing this information is probably going to be useful for part 2. And in case you're wondering, I'm not just saying that because I know what part 2 is. I did actually use this approach during part 1 because I figured it wouldn't waste time, and we would probably need to know this for some reason for part 2. Now moving on to part 2. Disintegrating bricks one at a time isn't going to be fast enough for what we're trying to do, so we're going to need a chain reaction. We'll need to figure out the best brick to disintegrate. So for each brick, we're going to figure out if we disintegrate it, how many other bricks would fall. And this includes a chain reaction, so it's not just how many bricks are dependent on it. Using the same example as above, if we disintegrate brick A, all of the other blocks would fall. And if we disintegrate brick F, only one other brick falls. And any other brick does not cause other bricks to fall when we disintegrate it, so in total the sum is 7. So we want to know for each brick what is the sum of the number of other bricks that will fall if we disintegrate it. So here again our total starts at 0, but this time what we're going to do is we're going to basically do something similar to breadth first fill. So we're going to import a deck again. And now when we begin, we're going to attempt disintegrating this brick. And so once we disintegrate brick I, the queue of things that are about to fall is everything that is solely dependent on it. So it's going to be a deck containing j for each j that is supported by I if the number of supporters of j is only equal to 1. And we're going to keep a set of all things that are going to fall. So falling equals a set containing just q, and this will also be our scene set to avoid duplication. So now while q, j equals q.pop left. So we will now, since j is falling, anything that is, we're no longer looking at sole dependency. We're going to look at everything whose dependencies all fell. So we're also going to include I in this. So falling dot add I. So now, instead of checking for sole dependency, we're going to look at everything that is currently supported by J. So for K in K supports VJ. So for everything that is supported by J, that is also not already falling. So this is where we normally say if K not in falling, but since we have sets here, we can just use set subtraction. It has marginal runtime, performance differences. So now we're going to check if K is no longer supported by anything. So if everything that supports K is within falling. So in Python, less than or equal to means subset or equal to. So this just says if everything that supports K is also in the set of things that are falling, then that means that K is no longer supported. So we're going to add it to the queue and add it to falling as well. And now we can just add the length of falling, and we're going to need to subtract 1 because of this. Actually, this is not necessary. It just occurred to me. The reason this isn't necessary is because... actually, no, it might be. Yeah, this might be necessary. And so if we run that, that now gives us part 2. So basically, to recap what we did for part 2, we rely on the fact that we already know which blocks support which, and we have a two-way map for that. And then for each block, when we try disintegrating it, we first load everything that is solely supported by it into a queue of things that are falling, and keep track of it in a set. The reason we also add I is so that for this check, if K is supported by I as well, we're not going to falsely say that it's still supported because I was already disintegrated. And so now we just loop through the queue. Each time we look at everything that's supported by J, those are all the things that could potentially start falling as a result. And for each of them that are not already falling, we check if all of its supports are now falling or gone, then we're going to add it to the queue and set of things that are falling. And then at the end, we just increase the total by how many objects ended up falling, minus 1 because I is disintegrated and not falling. And so that gives us our answer for part 2. So that's all for today's video. Thank you for watching, and I hope you enjoyed.